Welcome to Study Loop.
Okay, so for this question, we need to determine the stagnation temperature and the stagnation density of the argon gas first. Since we know the inlet velocity is very low, that means the inlet velocity is approximately equal to 0. So therefore, if T0 is equal to T1, which is equal to 293 Kelvin. And then we'll have stagnation density of the argon gas is equal to 1.968 kilogram per meter cube, since we know the gas constant for the argon gas is 0.2081 kilojoule per kilogram times Kelvin. So now we can determine the critical temperature and the critical density of the argon gas, since it was asking us the mass flow rate at a location which is when the mass flow rate is at the throat. Okay, because when the mass flow rate through the nozzles, it will touch the area of the throat. So now let's determine the critical temperature first. So we know critical temperature over T0 can be equal to 2 over K plus 1. So eventually we'll have the critical temperature is about 220 Kelvin. And the critical density over rho 0 is equal to 2 over K plus 1 to the power of 1 over K minus 1. And we know the specific ratio for the argon gas is 1.67. So eventually we'll have the critical density, or the density at the throat, is equal to 1.278 kilogram per meter cube. So now we can determine the mass flow rates at the throat area, or the mass flow rate through the nozzles, which is equal to rho asterisk times A asterisk and then times V asterisk. So we know the critical velocity, which is the velocity at the throat area, should be equal to the speed of sound at that location, which is equal to square root kRT asterisk. So therefore, we have m dot is equal to rho asterisk times A asterisk and then times square root kRT asterisk. So we know the area at the throats is 0.015 meters square, and we know all the other conditions from the previous calculations. So now we can plug in back to the equation to determine the mass flow rates, which is equal to 1.278 kilogram per meter cube, and then times 0.015 meter square, and then times square root 1.667 times 0.2081 kilojoule per kilogram times Kelvin, and then times 220 Kelvin. And then don't forget to convert it to meter square per second square. Okay, so we have times 1,000 over 1, and here unit is meter square per second square, and the unit below it is 1 kilojoule per kilogram. And this will give us the mass flow rates is about 5.3 kilogram per second. So now let's take a look at the options. So the correct answer should be C.